diffraction phenomenon. Diffraction is a wave phenomenon in which the apparent bending and spreading of waves when they meet an obstruction. Diffraction occurs with electromagnetic waves such as light and radio wave, and also in sound wave and water wave. Light diffraction is caused by light bending around the edge of an object. The interference patterns of bright and dark lines from the diffraction experiment can be only explained by the additive nature of wave, which when peak can add together to magnify the light, or a peak and the two will cancel each other out and result in darkness. Constructive interference is the result of synchronized light waves that add together to increase the light intensity, and the destructive interference results when two out-of-phase light waves cancel each other out, resulting in darkness.
X-ray sources. What is the properties of X-ray? X-rays are highly penetrating and invisible radiation. The wavelength range for X-ray is from about 10 to the power of negative 8 to 10 to the power of negative 11 meter. Production of X-ray is visible light photon and X-ray photon are both produced by the movement of electrons in atom. Electrons occupy different energy level or orbital around an atom nucleus. How does atom emit light? A collision with moving particle excites electron. This causes electron to jump to higher energy level. The electron fall back to its original energy level, releasing the extra energy in the form of light photon. X-ray can be produced in highly evacuated glass bulb called X-ray tube. This X-ray tube contains essentially two electrodes, which is anode and cathode. Anode made of platinum, tungsten of heavy metal of high melting point, and another electrode is cathode. How does X-ray produce is the electron coming from this side. When this electron come to hit this metal term, X-rays are emitted from this metal target and they go out of this window target. This is how X-ray produce their instrumentation. The applied voltage is 50 kV only. 2% conversion to X-ray goes as heating.
What is X-ray diffraction? All moves like a wave and like a particle share energy and momentum. They diffract when waves move through a crystal. The crystal diffract light, sound, atoms, neutrons, and electrons. X-ray diffraction is a non-destructive technique that provides a detailed information about the crystallographic structure, chemical composition, and physical properties of material. The diffraction depends on the crystal structure and the wavelength. X-rays are high-energy light with a repeated period called the wavelength. Since the wavelength of X-ray is similar to the distance between the atom in the crystal, a special interference effect called diffraction. It can be used to measure the distance between the atoms. Interference occurs when X-rays interact with each other. If the waves are in alignment, the signal is amplified. This is called constructive interference. If the waves are out of alignment, the signal is destroyed. This is called destructive interference. When the wavelength of the radiation is comparable with or smaller than the lattice constant, one can find diffracted beams in direction quite different from the incident radiation. The structure of a crystal can be determined by studying the diffraction pattern of the beam of radiation incident on the crystal. X-ray crystallography is a technique of crystallography in which the parent will display the diffraction of X-rays through the closely spaced lattice of atoms in a crystal. In this part, we will talk about the Bragg's law. Bragg's law helps us to calculate the interspace distance between layers of atoms. It uses X-ray diffraction to calculate the distance. we're gonna pass the first X-ray on this atom. Then it's gonna diffract at the same angle. Then we're going to have another X-ray coming at the same angle, striking the atom below it. So we call this angle as theta, which is going to be the same at here. So the hypotenuse of this triangle is here. The interspace equals the values of atoms. Say this part as y, z, and x. This is going to be the wave of the X-ray. Now we're going to say these two waves are in phase. The wave of the bottom, you need to realize it travels a greater distance than the wave on the top. The extra distance that it travels is equal to this right part of the triangle plus this part. On the left, that is xy, and on the second part is yz. So that is the extra distance that the wave on the bottom travels compared to the wave on the top. The extra distance is equal to the wavelength of the wave. It can also equal to n multiplied with the wavelength. So it's gonna be n multiplied with lambda, where lambda is the wavelength of the X-ray, and that could be times with n. Since it is parallel to each other, the angle of these are the same with the top.
Cubic crystal structure determinations proceed in three major steps. First step is the shape and size of the unit cell are deduced from the angular position of the diffraction lines. Second step is the number of atoms per unit cell is then computed from the shape and size of the unit cell, the chemical composition of the specimen and its measured density. Third step is the position of the atoms within the unit cell are deduced from the relative intensities of the diffraction lines. Size and shape of unit cell determination involves the accurate determination of peak position and determination of the unit cell parameter from the peak positions, consists Bragg's law, interplanar displacing, and systemic absence. Bragg's law happens when X-rays are scattered from crystal lattice. Miller indices are determined by the intersection of the plane with these axes. The reciprocal of these intercepts are computed and fractions are declared to give the three Miller indices. For example, a plane parallel to two axes but cutting the third axis. At the length equal to 1 each of a unit cell has Miller indices of 100, 010, or 001 depending upon the axis cut. And the plane cutting all three axes at length equal to the each of a unit cell has Miller indices of 1111. A beam corresponding to a value of n or more than 1 could be identified by statements such as the nth order reflections from the HKF planes. This order pattern is a direct result of two things. First thing is the size and shape of the unit cells, which determine the relative position of the diffraction peaks. Second thing is the atomic position within the unit cell, which determine the relative intensity of the diffraction peaks.